Hey guys, it's revision time again. So in this video, we're going to go through exercises on forces and motion. We're going to deal with acceleration, we're going to deal with impulsive force, and I'm also going to look at Hooke's law, forces in a spring, and finally I'll be looking at waves. We'll be going through these topics in exercises. Let's get started right away. If you're looking for other topics, please look at revision 1. I've done another revision video. Please have a look at it after this video. So let's go to the first question. Let's look at this question. A car accelerates from rest, so let's just underline the keywords, accelerates from rest at time t equals to 0 to maximum speed. Figure 1.1 shows the speed time graph for the first 25 seconds of its motion. So let's study the graph first. So this is the graph. We have the speed at 0 is 0 as stated in the question. And then you can see the speed increases, and the speed increases, and then finally it starts to decrease, and then it plateaus off. So this is our graph. Now let's look at the question. So the first question states that the mass of the car is 3,250 kg. For the time between t equals to 0 and t equals to 5 seconds, determine the acceleration. So first of all, what is acceleration? We have to remember that acceleration is the rate of change of speed. So it will be final speed minus initial speed over time. Now we could use the formula, but when we are given a graph like this is a speed time graph. For a speed time graph, the gradient will give us the acceleration. So you have to remember that. For speed time graph, acceleration can be found through the gradient. So that's exactly what we're going to do here. So first, when we are looking for gradient, I always advise my students to mark the points that we are going to use on the graph first. So they want from 0 to 5. So let's mark this point first. So this point here is 520. This way you will avoid careless mistakes. And of course the other one is the origin. So origin is 0, 0. These are the 2 points that we're going to use to find our gradient. Now we can find the gradient using y2 minus y1 over x2 minus x1. So let's do that. Here the acceleration a is equals to the gradient, and this will be equals to, so y2 minus y1, this is why I like to label the points first. Y2 is 20 minus 0, and x2 will be 5 minus 0. So this is equals to 20 minus 0 over 5 minus 0. And this will give us 4 meter per second square. And there's two ways you can write this. You can write it like this. You can also write this as 4 meter per second square. Both are correct. So the answer here for acceleration is 4 meter per second square. Now let's look at the next question. What is the resultant force acting on the car? So we have to remember Newton's second law here. Resultant force F is equals to ma, product of mass and acceleration. Resultant force equals to mass times acceleration. So here we have to substitute the mass and the acceleration. So the mass is given in the question. This is why we were given this earlier, 3,250 kilograms. So just substitute 3250. Acceleration we just found to be 4 meters per second squared. So times 4. And this will give us a value of 13,000 newtons. So 13,000 newtons is the resultant force acting on the car. Now let's go to the next part of the question. Using figure 1.1, describe the motion. So we are to describe the motion of the car between t equals to 7 and t equals to 14. So from 7 to 14 seconds, we need to describe the motion of the car. So first, let's look at the graph. So let's mark t equals to 7 and 14 first. T equals to 7 is here. So we are looking at this point here. From here to 14, 14 is here, so to here. So this is the section that we are looking at. Now we are supposed to describe the motion of the car here. How do we describe the motion of the car? So from here, you can see that the speed is changing. The speed is still increasing. You can see clearly from here. When it is 7, the speed is here, this value here. And then when it is 14, the value is here. So clearly there has been an increase in speed. If there is an increase in speed, definitely there is an acceleration. Now the question is this a constant acceleration or is it a changing acceleration, and how is it changing? So from the first question that we did, we already understand that the acceleration is calculated through the gradient. So let's try to look at the gradients here. So when we are looking at the curving point of the graph, the acceleration will be the gradient of the tangent to the curve. So let's take the first point here. Okay, let's take close to this point. So the tangent would be something like this. So the gradient would look something like this. This will be the steepness. Now look at nearer the end point, nearer 14. So let me use a different color here. So nearer 14, you can see the gradient has become like this, something like this. So this is not a good tangent. I'm not using a ruler here. This is just for visualization. So the gradient should be roughly like this. Now here, these are not proper tangents, by the way. This is just to answer the question generally. So you can clearly see that the gradient is decreasing. If we were to take the first gradient, this would be the gradient. And look at the second gradient. So you can see clearly the steepness is decreasing. Now the steepness represents the acceleration. Therefore we can say the object is accelerating from 7 to 14, but the magnitude of acceleration decreases. So it is moving with decreasing acceleration. So that's the answer here. So when we are asked to describe the motion, and we have to say that, first of all, the car is moving with decreasing acceleration. So how do we explain this? The gradient of the graph is positive, which indicates acceleration, but the gradient is decreasing, and therefore decreasing acceleration. Now let's look at the thrust on the car. What is the thrust? The thrust is the force that is exerted by the engine. When we have a vehicle that has an engine that drives the motion of the vehicle forward, then it is called the thrust. The force is called the thrust. So the thrust on the car remains constant from t equals to 7 to t equals to 14. Now let's just pause and think about this. The force that is driving the car forward is constant according to the question from 7 to 14. However, we just saw that the car is still accelerating. From 7 to 14, the car is still accelerating. It does not reach constant velocity yet. It is still accelerating, but the acceleration is decreasing. So, what is happening here? And that is the question. The question is, explain why the car moves the way it does, as shown in figure 1.1, from 7 to 14 seconds. So here we have to look at the car. Let's look at the car as I'm going to represent the car as a sphere. Now let's think about all the forces acting on the car. So first, of course, the car has mass. Anything that has mass, we definitely have weight. And then the car is on the road. Since it is in contact with the road, there will be a reaction force, a normal reaction that is perpendicular to the surface. So here, normal to the surface. And then we have the thrust force that is driving the car forward. And of course, as the car is moving on the road as well as from the air, we have resistive forces. So let's collectively put it backwards direction as Fr. This is to represent the resistive forces, F subscript R. So the resistive forces consist of two forces here, that is the air resistance and the resistance from the road. Now, what is going on? The thrust is constant. The force that is driving the car forward, the force that is propelling the car forward is constant. This is the direction of the velocity of the car. But the acceleration is decreasing. Now we have to remember the relationship with all the forces here. Remember that resultant force is equals to ma. So resultant force is directly proportional to acceleration. Now what is happening here to decrease the acceleration? So we know that the acceleration is decreasing. This must mean that the resultant force is decreasing as well. And what is causing the resultant force to decrease? So when we look at the direction of the car, the motion of the car, which is the car is moving this way horizontally, the resultant force will be equals to, the forward force will have a positive value, and then we have to account for the backward force as a negative value. So T minus the resistive forces here. So if you want to know more about this in detail, I will leave the link in the description below. I've done a video on resultant force. That will be a separate video. But this is how we get the resultant force. So the resultant force here will be the thrust minus the resistive forces. Now the thrust is constant. This does not change. So the only way that the resultant force can go down is if the resistive forces are becoming larger. So when you subtract a bigger value, and therefore the resultant force is lower, the acceleration is lower as well. So this is exactly what is happening here. We have to remember that air resistance is directly proportional to the velocity of the object, v squared in fact. So when the velocity of the object increases, the value of air resistance increases as well. So air resistance increases with speed. This will mean increasing resistive forces, which will result in decreasing resultant force and therefore decreasing acceleration. So this is how you tie everything together for this question. The next question, we are going to study Hooke's law. So we're going to study forces in springs. Let's look at this question. Now, figure 2.1 shows a piece of equipment used by athletes that consists of 5 identical springs between 2 handles. So as we can see in the diagram here. Now the original length of each spring is 0.54 meters. So the original length, meaning the unstretched length, the length before any force is applied is 0.54 meters. So let's just label that as L naught. This is equals to 0.54 meters. Now 2 athletes pull on the 2 handles of the equipment in opposite directions. So what's happening here is forces are being applied on both sides here as well as here. 2 athletes are pulling on opposite sides. Now the spring in the equipment obeys Hooke's law. The springs obey Hooke's law. Explain what is meant by this. So what does it mean when a spring obeys Hooke's law? Hooke's law simply states that the extension of each spring is directly proportional to the force applied to it. In this case, it's the tension force. So the extension of each spring is directly proportional to the tension applied. This is Hooke's law, very simply. So F is directly proportional to X. This is Hooke's law. Now how do we make this an equation? Of course, we add the constant of proportionality, which is K, which is the spring constant. F is equals to Kx. But when we are explaining Hooke's law, we use this relationship. F is directly proportional to X. So let's go on. Each athlete pulls the handle towards himself with a force of 1,500 newtons. Calculate the tension in each spring. Okay, so there are 2 things to consider here. First of all, let's sketch this out first. So you have the 2 handles on both sides. Then you have the 5 springs. Now you have forces here acting 1,500 newtons on this side as well as 1,500 newtons on this side. Now the first question you should ask yourself is, what is the total force acting on all the springs? So is it 1,500 times 2 or is it 1,500? Now here you have to understand tension force. Tension force is a pulling force inside an object such as a spring or a rope or a string. When you tug at it, when you pull, then you create a tension force here. So what is the tension force in the spring? The total tension force acting in the spring is actually 1,500 newtons. It does not double up because tension acts in both directions here. We can talk about the tension force that is pulling in this direction, pulling this side, acting on this side, so acting on the athlete on the right, which will be the same as the tension force that is acting towards the right, that is pulling on the left handle, athlete on the left. So actually the tension force, the total tension force in all the 5 springs is just 1,500 newtons. Now in this case, the strings are arranged in parallel. So when the strings are arranged in parallel, they are sharing the load. They are sharing the force. The force is evenly distributed between the 5 springs. And so, let's answer the question here. Calculate the tension in each spring. So first of all, when we are talking about tension in one spring, 5 springs, the tension is 1,500. Therefore, the tension in each spring, we just have to divide it equally because it's arranged in parallel, the load is shared equally. So tension will be equals to 1500 divided by 5, which is 300 newtons. So this is the tension in each spring. Now let's look at the second question. The length of the equipment is now 1.02 meters. So after the two athletes are pulling it, the length is now 1.02 meters. With the force, remember the force in each spring we just calculated is 300 newtons. So the question here is, so this is the new length. The question is to find the spring constant, which is K, of each spring. So here of course we are dealing with springs and we are looking for spring constant. Definitely we are going to use the formula F is equals to Kx. This is from Hooke's law. So F is equals to Kx. Rearranging K to be the subject of the equation, K is equals to F divided by X. Now the force acting on each spring we just calculated earlier to be 300 newtons. So this will be 300 divided by the extension. So what is the extension? The extension is the length after the force is applied minus the original length minus the unstretched length. So here both are given to us. The question says that after stretching it is 1.02 and the original length before stretching is 0.54. So the extension would then be 1.02 minus 0.54. So key this into the calculator and you will get 625 Newton per meter. This is the spring constant. Here you just have to take note of the units that you use for length. The extension here we use meter. Therefore, it is Newton per meter. If it was centimeter, then it will be Newton per centimeter. So this is how we get the spring constant. Now let's go to the next part of the question. State the energy changes that takes place as the two athletes stretch the equipment with their muscles. So here we are talking about energy transformation from using muscles to moving the spring and getting it stretched and in that position. So we are starting whenever we start with energy that comes from organic beings, we are looking at chemical energy. And when the spring is stretched, of course the spring now contains, the final energy here is elastic potential energy. So the change in energy is from chemical energy to elastic potential energy. Now let's look at a question on impulse. A paintball marker, this is the equipment we use when you're playing paintball. A paintball marker exerts an impulse of this much on a pellet as it is fired. Define impulse. So what is impulse? Now in physics, definition is very easy. All you have to do is look at the formula. So what is the formula for impulse? Impulse is equals to the change of momentum, final momentum minus initial momentum. This is also equals to force acting on an object multiplied the time that the force is acting on the object. So you could use these two things to define impulse. So I've written down both here. Impulse is either the change in momentum or force multiplied by time, the time which the force acts on the object. So this is impulse. Now, the mass of each pellet is this. This is the mass of the pellet. Determine the speed of the pellet as it leaves the paintball marker. So as the paintball leaves the paintball marker, determine its speed. Now, let's review what we have here. We want to find speed. Impulse is given to us earlier. This is the value of impulse. 0.081 Newton second is the impulse. So all we have to do is use the formula for impulse, that is I is equal to, this time we want to relate it to speed. Therefore, we don't use Ft. Instead, we use mv minus mu. Now, the initial speed of the pellet is 0 because it's not moving. When it's inside the paintball marker, it doesn't move. Therefore, since u is 0, then mu will be 0 as well because mass times 0 will get 0. So all we are left with is I is equals to mv. And since we want v, we make v the subject of the equation. V will be equals to I divided by m. So we do have these two values already provided to us in the question. So all we have to do is substitute inside. So I is 0.081 Newton seconds over the mass here is 9 times 10 to the power minus 4 kilograms. This is all given to us in the question. So the answer that you will get here is 90 meters per second. So again, meter per second, you can also write this as 90 meter per second. Both are correct. So this is how we find the speed of the ball. Now let's go to the next part. The kinetic energy of the pellet as it leaves the paintball marker. So whenever we want to find kinetic energy, we use the formula. Kinetic energy is equals to half mv square. So we already have m given to us in the question, and we just found the speed as it leaves the marker. So this will be 1 over 2 times 9 times 10 to the power minus 4 times v square. So v here is what we just found, that is 90 meter per second. So 90 squared. After you key this in the calculator, you will get a value of 3.645 joules, which is equals to 3.6 joules in two significant figures. So this is the kinetic energy of the pellet as it leaves the paintball marker. This next question is about waves. Let's look at the question. Figure 4.1 shows a loudspeaker which produces a sound wave with a frequency of 12,500 Hertz. So this is the frequency of the sound wave produced. So here you can see the loudspeaker, you can see the cone outside. Describe how the sound is produced by the cone. So how the sound is produced. Now here with loudspeakers, of course we have to go a little bit into electromagnetism, but we're not going to go into that in detail here. Now when a loudspeaker produces a sound through the cone, what happens is the cone is going to vibrate. The cone is going to move back and forth, so it's going to vibrate. So it starts with that. Now for the cone to move in two opposite directions continuously, the loudspeaker must be connected to an alternating current source. The current supplied must be AC, it cannot be DC. If it is DC, then the cone will only move in one direction. So if we want it to move back and forth in two opposite directions continuously, then we need to connect it to an AC source. So this is how we start our answer. First of all, we need to connect it to an AC source. So once you connect it to an AC source, what's going to happen is the cone is going to vibrate. So the cone is going to vibrate, and the vibration of the cone. Now, as the cone is vibrating, what is going to happen is this vibration is going to be transferred to the layer of air that is just at the surface of the cone. So as it vibrates, the vibration is transferred to the layer of air. Now, as the air vibrates, then the air is going to transfer the vibration to the layer of air next to it, and then next to it, and next to it, and next to it, and that is how the sound wave is produced. Now, how do we write this down? So this next point will be, so the vibration of the cone is transferred to air particles on the surface of the cone, which is then passed on to neighboring air particles. So the air particles, the next layer, and the next layer, and the next layer, and then this creates compressions and rarefactions with the air vibrating at 15,000 Hertz. So when the air vibrates at 15,000 Hertz, that's when you will hear the tone, the sound wave. Right? So this is how the sound is produced. So remember compression and rarefactions. This is for longitudinal waves. What happens is there will be regions where the air, there you can see the lines are further apart, and then you will see regions where they are close together, and then further apart again, and then close together, and then further apart. So the regions where they are close together, these are called the compressions, and the regions where they are further apart, these are known as rarefactions. Now these are the parallels to crest and trough. So when you have a transverse wave, we have crest and we have trough. But here we don't have crest and trough, we only have compression and rarefactions. Right? So this is how sound is produced. Now let's go to the next part. The speed of the sound in air is 330 meters per second. Speed of sound is given to you. What is the wavelength? So let's recall, we have the frequency. Frequency is 12,500 Hertz. And now we have the speed. V is equals to 330 meters per second. So I hope you know what formula you need to use. We have V and we have F. Of course, we need to use V is equals to F lambda. This is the formula for waves. V is equals to F lambda. Now we want to find the wavelength. Lambda is the wavelength. So rearrange lambda as the subject. Lambda is V over F. And this will be equals to, the speed is 330 divided by F, 12,500 Hertz. And so the answer that we will get here is, just use your calculator, you will get 0.0264 meters. This is the wavelength. Now let's go on to the next question. The sound from the loudspeaker passes through a gap between two walls. Alright, so the gap has the same width. This is a very important point. Gap has the same width as the wavelength of the sound. The two walls are as shown in the figure. So you can see the two walls here. So the sound is going to pass through the gap from left to right. Now let's see the question. On figure 4.2, show how the sound wave travels. Show how the sound wave travels towards the walls, through the gap, and away from the walls. So all the way from the beginning to the end. Represent the sound waves as a series of wave fronts. So we are just going to use lines to represent the wave fronts, and we're going to travel through the gap. So first of all, let's think about what is the phenomenon that is involved here. The phenomenon of wave that we are talking about here is, of course, when a wave passes through a gap or around an obstacle, then the wave will undergo diffraction. So here we are talking about diffraction. For diffraction to occur, always remember the wavelength of the wave must be approximately equals to the size of the gap. It must be around the same. Otherwise, the diffraction will not be so obvious. So first, let's draw the waves that are coming before it goes through the gap. So let's draw one here. Now when you are drawing waves, it's very important to draw the correct wavelength. You must reflect what is happening to the wave. So for example, if the wavelength doesn't change before and after, then you must draw constant wavelength. So I'll show you how to do that. Now the wavelength, the question says the wavelength is the same as the width of the gap. So you roughly know this must be the length of your wavelength. So roughly should be about here. So draw at least 2, 3 should be fine. Okay, so what is this wavelength that I'm talking about? Where is the wavelength? So remember, the wavefront represents the crest. Wavefront is a row of crests. So when you want to see wavelength, this is the wavelength. The distance between two consecutive lines. This is the wavelength. So the wavelength must be constant here and here. It must be the same. Alright, roughly the same. So now this is before it goes through the gap. What happens after it goes through the gap? Of course, after it goes through the gap, we know diffraction has occurred. So it is going to spread out. Diffraction is when the wave spreads out. How does it spread out? When it spreads out, you start to curve. Now keep in mind here again, wavelength must be constant. After diffraction, the frequency remains the same, the wavelength of the wave remains the same. The only thing that changes is the energy is more spread out. Therefore, the amplitude of the wave will decrease. However, the frequency and the wavelength remains unchanged, and that must be reflected in your diagram. So let's draw this. So this diagram is here. And then one more here. Okay, so again, the wavelength must be fairly constant here. You don't have to label the wavelength like this. I'm just labeling it to show you that it must be about the same before and after. So this is how we show diffraction. That's it for this revision video, guys. If you've learned something, please do me a favor and hit that like button, because it really does help. It tells the algorithm that this is a good video. If you want to cover more topics, I have covered other videos as well. So I have another revision video. I'll leave the description, the link below. You can check it out now. And if you're watching this, probably your exams are nearby. So all the best to you, and I hope to see you in the next video.